All right, so let's continue where we left off in the last video. So we are now on our topic of energy. And we have been talking about, and the very last topic was this idea of heat, where we can calculate heat by looking at a substance mass, their specific heat capacity, that is how much energy you need to raise a certain gram, so weight right there, certain gram of thing by certain degrees Celsius, and delta T. Remember, delta, anytime you see delta, means change. And it's always going to be final minus initial temperature. And we looked at this question where we have water loses energy and it loses temperature. Now we can use this idea of how much heat are releasing, or this equation of Q, when we are doing energy transfer. So when we put two objects of different temperature next to each other, they're going to transfer energy until they're both the same temperature. And we all know this. You put something hot next to something cold, the hot thing loses energy and cools down. The cold thing gains energy and heats up. And so what our equation is saying here, if we put a metal into water, the heat, so let's imagine that we put cold metal in hot water. So the heat gained by the metal, Q metal, is equal to the heat lost by water minus Q water, right? So this is our conservation of energy again. Where if the water has a higher temperature than the metal, right? The water is going to lose heat, and all of the heat loss is given to the metal. So that's why we have this equal sign here. The heat gained by the metal is equal to the heat lost by the metal. And we already know equations for Q. So the Q metal is the mass of the metal multiplied by the heat capacity of the metal multiplied by delta T of the metal. And that is equal to minus water, our mass water, CS water, delta T water. Now, in this equation, while we're setting the two heats to each other, temp final is the same for both the water and the metal. That's because they're in contact, so they're going to reach what is called thermal equilibrium, which is a fancy way to say they have the same temperature, or they will have the same temperature. So here's this problem. This type of problem I love to give on the test, which means, yeah, you're probably going to get a problem like this on the test. So make sure you know how to use this equation. Make sure you know how to do this. Just do examples like this, and you should be able to get it. But here's your first example. Pause the video, try it out. Don't wait for me to just give you the answer. But I'm going to jump into the answer right now. So here, this equation, we have 6 variables. So just like PV equals nRT, what we're going to do is we're going to fill in the variables and see what variable is missing and solve for that missing variable. So silver block CS of 0.235. So my metal, the CS is 0.235. Initially, actually, we have more than 6 because it's T final minus T initial. T final minus T initial here. Initially, the silver's at 58.5. We submerge it into 100 grams of water. So that's my mass of the water. Do not forget the negative sign. Otherwise, this equation won't work. And the water is initially 24.8. The water has a CS of 4.18. The final temperature of the mixture is 26.2. So that's going to be the same in both. What is the mass of the block? All right, so this is algebra. Get mass of metal by itself, solve for mass of metal. So Without plugging in numbers, mass of metal is going to equal negative mass of water multiplied by CS of water multiplied by delta T of water divided by CS of metal multiplied by delta T of metal. Right, so we're solving for mass of metal. Plug all your numbers in. And what I got for that is the metal is 77.1 grams. Now, if you got a negative number for that, you should pause and think if you're to yourself if a negative mass is possible, which is not. Weight can only be a positive number. So if you got a negative number, that means you forgot that minus sign. So although that equation, I think, seems difficult the first time you see it, if you can do one Q calculation, all you have to do is set the two equal to each other and you'll be able to solve this type of equation. All right, so we've been talking about heat exchange. Now we're going to go to work and we're going to go to pressure volume work, which is if you're expanding or shrinking your volume against a pressure. So basically you're not in a vacuum, you're on anything other than a vacuum. So like here on Earth, you do work, right? So if you're inflating a balloon, the balloon is pushing against the atmosphere to inflate. So the gas inside the balloon is doing work. And our equation for that is work equals negative P delta V, which is external pressure and change in volume. Again, final minus initial. The only tricky part to this equation, which most of you, well, not most, some of you will forget, is that the pressure needs to be in atmospheres. The volume needs to be in liters because work is energy. The unit of energy is the joule. And we can convert between atmosphere liter and go to joules, but it has to be atmospheres liter. Now, if the volume is expanding, work is positive because you're doing it on the surroundings. Or sorry, yeah, that didn't make sense. So when you are expanding, right, you are pushing against the atmosphere, like I said. When you do that, you lose energy because you are working to push the gas away from you. So although delta V would be positive, there is that negative sign here. So work is negative. If you're shrinking, then the surroundings are doing work on you and you are gaining energy. So here's a simple question to try this out. See if you can figure it out. It's not that hard. I believe all you can do it. And last, after you figure out the math of it, tell me, was this endothermic or exothermic? See if you remember those phrases. So I'm gonna hop right into it. Piston cylinder absorbs 565 joules of heat. All right, so here we have to remember our delta E equation. So delta E equals Q plus W. So I'm absorbing heat. That means if I'm a piston and I'm absorbing heat, heat's going in. So that's a positive number. I'm gaining that heat. So it's 565 joules. Now, let's take a look at work. I'm expanding from initial volume of 0.1. So delta V equals V final minus V initial. My initial is 0.10. My final is 0.85. My delta V equals 0.75. The external pressure is 1 because I like to make it easy for you, even though you might not believe it. So it's going to be 1 times 0.75. Work equals negative 0.75. Don't forget the units. Let's see, our external pressure was in atmospheres. Our delta V was in liters, atmosphere liters. Now I can convert to joules. 1 atmosphere liter is 101.3 joules. So my work here is negative 75.9755. So 565 minus 75.9755. Because remember, we're asking what is the change in internal energy? That's equal to 489. This is the positive number, which means energy is ultimately flowing into the system, means it's going inside. So it's endothermic, endo. Here we have another type of question that has to do with energy. And this one's kind of like a harder cumulative question. So see if you can tell me how much energy is being released through combustion here. So we haven't really touched on this all that much, right? But we are blowing acetone up. And if we blow 1 mole of acetone, we get this much energy. But I'm saying we have 177 milliliters of acetone. Here's the density of acetone. So I want to know how many kilojoules are released when we blow up that much acetone. So don't look at your work equation. Don't look at your heat equation. We're doing something else here. We're doing delta H, which is change in enthalpy. That's what H stands for. Enthalpy is a fancy way to say heat. So we're looking at change of heat for a reaction, which in chemistry, you really don't work with Q's, you work with H's. We don't go into why that is Gen Chem 1. But yeah, see if you can puzzle this one out. This is a big unit conversion. So take some time to do this. And hopefully you took that time. So let's solve it. First, I need to know what is the weight. Well, really, what I need to figure out is how many moles of acetone I have. The reason why I need to figure that out is because I know how much energy I release for 1 mole of acetone. The question is, in my scenario, how many moles of acetone do I actually have? So I'm given a volume and I can convert to weight by a density using our nifty train track. So I have 177 milliliters. For every 1 milliliter, I have 0.788 grams. Then I need to look up the molecular weight of acetone, because hopefully you have not forgotten that to go from moles to grams or vice versa, you need molecular weight. So acetone is 58.05 grams for 1 mole. And this amount of acetone we have is 2.4 moles. So I need to know how much energy do I get out when I blow up 2.4 moles of acetone? Well, I have 2.40 moles. Here's my conversion factor between kilojoules and moles. For every 1 mole, I have negative 1790 kilojoules, which is negative 4,300. Negative 4,300 kilojoules. And hopefully by now you've figured out that the division sign in our units here is the same line I do for my train tracks. That's why moles on the top, kilojoules on the bottom, because they're split like that. You can always do the opposite. You could do moles on top, negative 1790 kilojoules. It would be 1 because the denominator is always 1. But yeah, that's how much kilojoules are released when you blow up that much acetone. And that ends this PowerPoint. So I'm going to switch PowerPoints here. And we're going to continue what we just talked about with the acetone and talk about the idea of calorimetry. And more specifically, we're going to start with bomb calorimetry. So the way we know how much energy stuff has, and by stuff, I mean like Butterfingers or a piece of bread, what you can do is you take whatever it is, you want to know how much energy it is, and you literally blow it up. And you blow it up in what's called a bomb, which more specifically is called a bomb calorimeter, which is shown here. So here's our sample that we want to blow up. It's in a chamber, and you have a fuse that runs down here. and you have a little wire that creates a spark between the fuse. The oxygen catches fire and blows up your sample, all right? So this, when you blow up your sample, you're releasing heat into just this, you're just releasing heat. And surrounding this canister is water. Hopefully you know the law of energy, where energy cannot be created or destroyed. So that heat has to go somewhere, and it's absorbed by the water. And we have a thermometer in here, so we can tell how much the thermometer raised by, which is directly proportional to how much heat was released, which is directly proportional to how much energy our substance has when we blew it up. And we have all the tools to do that already, all right? And that's shown down here, right? The change in energy of our system, that is how much energy is in here, that's delta E system, is directly related to how much heat is released. The reason for this is because we're doing this at constant volume, so there is no work, right? Remember, work equals P delta V, negative P delta V. Here, it's a constant volume, so delta V is 0, so work's 0. Remember, energy equals heat plus work. Well, if work is 0, we can simply say energy is heat. This is why this equation works. All right, so delta E system equals the heat of the reaction, right? And so we are releasing heat. So negative Q reaction is equal to the heat absorbed by the calorimeter. And the heat absorbed by the calorimeter is equal to a constant multiplied by delta T. So what we do in the experiment is that we calculate delta T, and we know C calc already. That's a constant. And we get Q calc. From there, we can calculate Q reaction. From Q reaction, we can calculate delta E system. A lot of parts, and I'm sure it's very confusing the first time you hear it, but let's take a look at try and solve a bomb calorimeter problem. So here I have an example where we're blowing up mothballs. Read through it, see if you can use logic to figure it out. Always feel free to go back to what I was just talking about. All right, so let's take a look at this. Mothballs are made of naphthalene. We have 1.025 grams of naphthalene. We burn in a bomb calorimeter. The temperature rises from 24.25 to 32.33. So that's delta T, right? Our temperature is final is 32.33 minus 24.25. What's delta E reaction in kilojoules per mole? Okay, so I want moles. So I know I'm going to use that weight somehow. So let's just do that first. How many moles of naphthalene do I have? So 1.025 grams. And for every 128.17 grams, I have 1 mole. And let me just calculate that out using Excel here. So that's equal to 1.025 divided by 128.17, which is 0.007997. So we have 0.7997 moles. All right, so I want the answer in kilojoules per moles. I just found out how many moles I have. Neato. Now we got to find kilojoules. Right. Okay, the heat capacity of the bomb is 5.11 kilojoules per centigrade. Look, a kilojoules. So I just need to get rid of the centigrade. Oh, look, temperature in centigrade. I can get rid of the centigrade. So 5.11 kilojoules for every centigrade. Here's centigrade. Whenever I say centigrade, that means Celsius, by the way. So let's calculate how much energy the calorimeter absorbed. And that is calorimeter absorbed 41.0 41.3 kilojoules of energy. That means that our explosion released negative 41.3 kilojoules of energy. Remember, I want it in kilojoules per mole. So in total, we had, whoops, that's supposed to be 0.007997. I'm sure you're yelling at me, just like you do in class whenever I make the slightest calculation error. I appreciate that everybody lets me know about it. I'm not being sarcastic there. That tells me you're listening. All right, so the energy released from mothballs are negative 5162.913 kilojoules per mole. Sig figs though, 3 sig figs, so negative 5.16 times 10 to the 3 kilojoules per mole. And in case you're wondering how I do the scientific notation, basically every time you move the decimal 1 to the left, you gain a power. So this is 10 to the 1. Do it again. 10 to the 2. Do it again. 10 to the 3. Right. And I only want 3 sig figs. It's negative because we are exploding something, right? So it's exothermic. When you explode something, you feel the heat. And also because Q cal was positive and Q cal equals negative Q reaction. So that's our bomb calorimeter problem right there. Now let's look at something you're actually going to do in the lab, I believe, either for Gen Chem 1 or Gen Chem 2. I don't quite remember which one it is. And that's coffee cup calorimeter, which here we are having a reaction done in water. So it's similar to the bomb, except we're not blowing stuff up. But it's the same logic. Some reaction happens in our cup. That is either absorbing heat, or sorry, releasing heat or absorbing. We don't know which one. It can be either. But what we do is we measure the temperature of our water. So water's in here surrounding our reaction. And so we know the weight of the water. We know our heat capacity of water. So we watch the thermometer to calculate delta T. And we call this Q solution. And just like the bomb calorimeter, the heat absorbed or released by the solution must have come from the reaction. So once we know Q solution, we know Q reaction. And once you know Q reaction, you know what's called delta H. So I mentioned this already in this video. Delta H is called enthalpy. You don't really need to know what that is, other than it's a fancy way to say heat. There's a lot more to it than that. Don't worry about it right now. But no, if I say coffee cup calorimetry, and if I ask delta H reaction, really I'm just asking for Q reaction. They're the same number. Again, we don't need to know exactly why that is theory-wise. Just make sure you do know that. So here is a question that tests your mastery of this idea. To get your feet wet, try that. And then let's look at the answer. So I'm going to start with the answer now. So please pause if you haven't tried it yet. So we have instant cold packs, blah, 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 blah. So actually, I should read it because it's cool. So instant cold packs, you crack. It's a container where you more or less crack it. And what you do is there's a small plastic divider in the cold pack. And when you crack it, you break that divider and you let the two substances mix. Or in this case, what you're doing is you're putting a solid with water. And when you mix that solid, it's going to dissolve into ammonia and nitrate. And this will absorb heat. So this reaction absorbs heat. And so if you put it on your skin, it feels cold because it's taking heat from you. So I want to know, what is delta H? Remember, delta H is enthalpy. What is delta H for this reaction? When 1.25 grams of NH4NO3, ammonia nitrate, is dissolved in enough water to make 25 milliliters of solution. My initial temperature, so let's look at our equation here. So mass of solution, I don't have that yet. CS solution, I don't have that yet. delta T, I can start filling in. My initial, remember it's final minus initial. My initial is 25.8. The final is 21.9. So delta T is right there. So I want kilojoules per mole. All right. So I already gave you a weight of ammonium nitrate. So we're going to do the same thing we did for the bomb. And let's just convert that to moles to begin with. So I have 1.25 grams. And 80.043 grams is 1 mole. Let's do this. Equals 1.25 divided by 80.043. So the amount of moles of ammonium nitrate I have are 0.0156 moles. Right. So, oops, don't want to do that. Use 1.02 grams per milliliter as the density of the solution. All right. Now we can calculate mass of solution, right? Because I have 25 milliliters. The density is 1.02 grams per milliliter. Milliliters cancel out. So this is 25 times 1.02. So the weight of our solution is 25.5 grams. So mass is 25.5. Multiplied by CS, 4.184. Hey, look, we have everything we need. So let's calculate Q reaction, or rather, we're going to calculate Q solution. So Q solution is equal to negative mass, so negative 25.5 times C of solution, 4.184 times delta T, final minus initial, 21.9 minus 25.8. So Q solution is 416, right? Now, I already incorporated the negative sign here. What some of you are going to be tempted to do is once you see this 416, you're going to say to yourself, but shouldn't that be negative? Shouldn't this be negative 416? Not so. The way I did the calculation on my calculator, rather Excel, is I already incorporated the negative. So this number is actually Q reaction. So if you incorporate the negative sign into your calculator, then you don't have to do anything else. That's Q reaction. Q reaction is delta H reaction. But let's look at our units so far, right? Our units for our heat capacity of solution is in joules per gram centigrade. So this 416 is 416 joules. And let's look what I'm asking for. I'm looking for kilojoules per mole. So I need to convert that. There are 1,000 joules in 1 kilojoule. So this is 0.416 kilojoules. I'm looking for kilojoules per mole. What do you know? We already solved for moles. So this is 0.416 divided by 0.0156. So the energy release, or absorbed rather, is 26.7 kilojoules per mole. Again, a lot of moving parts, but it's really just one equation, and it's the Q equation we've used about 3 times now. So hopefully it's starting to make a little more sense of how to do this. Here's another question. And what I'm going to do for this is I'm going to leave this as practice. All right. You practice this on your own. And on Monday, I will release the answer. Just the answer, not the work. So this is a good way to test yourself. And I think I'm going to pause there. So yeah, try question 3, see if you get it. Otherwise, if you have questions about anything, let me know, and I will get back to you when I can. Otherwise, I will see people. I will 99% certain unless something else happens, I'll be there on Monday. So I'll see people Monday. So I hope you have a good rest of your weekend, everybody. Take care.